And you know what? I think I'm going to project it. Now, I know sometimes there's a glare, but you guys have to deal with it. So I'm going to write on the board. So, all right. So on table H, what is the vapor pressure again of propanone at 50 degrees? What did we say it was yesterday? About 82, 83? All right. And what did we say the vapor pressure of ethanoic acid is? About 8?
Yeah.
Right? So make sure you know how to read table H. So if we go to 50 degrees here, we go up to ethanoic acid right here, and we go here, that's about 8. If we go up to propanone, okay, and look here, that's about 82, 83. All right? So now the question is, who has stronger forces? Ethanol or water? So we learned yesterday, propanone has the weakest forces, ethanoic acid has the strongest. So what about ethanol and water? Who's stronger? Who has stronger forces? Ethanol or water?
Water.
Water. How do you know? Cuz. What? Give me a reason. Well, okay, how do we know this has a lower, stronger force of attraction? How do we know this has weaker?
Wait, I have an explanation.
Go ahead.
At 50 degrees Celsius, ethanol has a higher vapor pressure.
Oh. Yeah, it's about 10, 20, 30, right? 30-ish?
Yeah.
So what does that mean if it has a higher vapor pressure?
If it was in a closed container and you're heating it up, it's gonna more, oh, I can never explain what I have to say. More of the ethanol will be evaporating.
So more of that word.
To more vapor, yeah.
Right, so if there's more vapor, so ethanol is evaporating more, just like the acetone on the one on the right completely boiled away. So there's more vapor, and if there's more vapor, there's more... What is this supposed to be?
Them colliding.
Colliding! So if there's more vapor particles colliding, and that's more vapor pressure. So I can't stress enough, if you have a liquid, and there is a lot of vapor coming off of that, okay? So with the levels dropping very quickly, like you just saw, there's a ton of vapor pressure up here. If you have a liquid with just a little bit of vapor, and it takes a long time for the liquid to drop, there's not much vapor here. So the higher the vapor pressure, the weaker the forces. I think you're starting to come around to that, and that's an important concept. Some kids never get that. So if you can get that, that really helps you understand, what we're learning about here, and forces of attraction. Because both of these are being held together, right? Shaking hands was the analogy. So they're all holding hands here. So to break free, they have to let go. And if it's easy to let go, then they can vaporize. Okay, now, the next thing we're going to learn about this is what's the deal with this right here? What's that dotted line all about? And this is where we're going to write some notes.
Standard pressure.
Standard pressure, good. Write this down. So, we're on table H. Dotted line represents standard pressure. What is that in ATM? What is it? 1 ATM, good. Now, what happens at this point, this point, this point, and that point? Don't answer out loud. Hand's tingling a little bit.
Oh boy.
It's just because it's really, acetone dries your hand out. Good thing I didn't do my nails today. Anyways, so what happens at those points where the solid lines are crossing the dotted lines? That's what I'm circling there. When those liquids, propanone, ethanol, water, ethanoic acid, cross the dotted line, maybe look at water and see what happens there, what temperature that is, and that should help you understand what happens at that point. This is really important to understand. So dotted lines represent standard pressure. When the liquids, again, these notes are under table H, right? We were talking about table H. When the liquids cross the dotted line, it's called this, blank. I think that would irritate me if I forgot to do that. And we're rolling. Anybody? Nicole?
The liquid turns into a gas.
Yes, but it does it all at once. So yesterday we learned that just the surface evaporates. At this point, any particle in here can evaporate. Down the bottom, middle, top, wherever. Any of them can evaporate because this is happening. I'm going to give you another piece of advice. Look at the temperature. I already said it, but I'm going to say it again. Look at the temperature where water crosses the dotted line. So what happens when these liquids cross that dotted line? They're boiling, right. That's the boiling point. It's called the normal, put normal in quotes there, normal boiling point. Normal boiling point. So, Watson, my dear Watson, what is the normal boiling point of ethanol?
Around 77 or something.
Yeah, I'd say it's close to that. 70, I think technically it's 79, but that's really close to the 80, right? So 77 to 80. So this point right here, we'll just round up, about 80 degrees Celsius. We know water is 100 degrees Celsius, okay? Someone tell me what ethanoic acid is, someone tell me what propanone is. That's acetone, we just saw it, but again, it's superheated, so it was a little confusing there. That was crazy, that's never happened before. You witnessed history right there for Mr. McCoy. Go ahead, look those up, raise your hand. What's the boiling point of propanone? What's the boiling point, again, normal boiling point of ethanoic acid, normal boiling point of propanone? Aaliyah, thanks for volunteering. Which one are you going to tell me? Which one? You telling me this one or you telling me this one? Propanone. Okay, what is that temperature right there where it crosses? About? Let's try again. What is, if you look at the x-axis, what does each line represent? So you go from 50 to 75. Each line must be. You with me, Leah? Sort of. Can you look up here for me? So if we're here at 50, and this is 75, this must be 55, 60, 65, 70. So if this is 55 and we go up, I would say that's pretty close to 55, maybe a little bit below, right? Or I mean a little bit above. So I'm going to say that's about 55 degrees Celsius. With me on that? Okay. So who can give me this one? Ethanoic acid.
117.
Yeah, sure. 117 degrees Celsius. All right. Why did I show you that demo? Why am I explaining this except besides the fact you need to know how to read this? It's a reference table. You need to know how to read it. We read the vapor pressure yesterday, reviewed that today. Now we're looking at boiling points. So why did I show you the demo? Why am I showing you the boiling points? Who can connect the dots here? Why am I doing all this? What am I trying to show you? What are you trying to learn here? Watson.
Different boiling points of different substances.
Good, which means you can determine or guess what else about the liquids. So if something boils at a really low temp, that literally spilled all over my hand, didn't hurt at all. If this spilled on my hand, it'd probably hurt. So, you're right, very good. But what am I really trying to show you here? That the boiling point of the liquid is a good indication of this. The forces of attraction, right. The lower the boiling point, the weaker the forces. That's what I was trying to show you. So I can show you the chart, and we can talk about this all day. You know, it's really super exciting, I'm sure. But I wanted to show you, like literally, show you liquids boiling so I could relate it. So you saw this boiling. That was the one that got all over me. You saw water, okay? And you saw the big difference in temperature. It's 50 degrees difference. The weaker it is, the lower that temperature is going to be. That should make sense to you, that it's going to all evaporate and boil very quickly if it's held together weakly. So the weaker the forces of attraction. So hopefully that makes sense. We talked about it yesterday. And I think, I get a feeling you guys are with me. All right, so where's that come into play in the reagents? They might give you 4 liquids, liquid A, B, C, and D. They'll give you 4 boiling points, and the question might say, which liquid has the strongest forces of attraction? Explain. So you would look at the chart, and you would pick the one with the highest temperature, and you would say, has the highest temp, therefore has the strongest forces. Done. Full credit, moving on. All right, so hopefully, again, that makes sense to you that if the particles, again, the holding hands analogy, if you're really holding on tight, okay, if you have like an iron grip, you're not letting go, it's going to be hard to remove that, right? So the particles are going to hang on much longer. That's why it needs more energy to boil, all right? So the reason that's called, what did I just do it? The reason this is called normal boiling point is because it's at standard pressure. So now what we're going to talk about, instead of normal boiling point, we're going to talk about just straight up boiling point. So normal boiling point is at standard pressure. Boiling point, let's define this. Boiling point is when, and this is the definition of boiling point, it has nothing to do with temperature or heat. Monday I'm going to show you how to boil water without adding heat. I don't have time today. Boiling point. This is the temperature at which the air pressure equals, you know what, I'm going to turn this off for a second, I'll come back to it here for a minute, where the air pressure equals the vapor pressure. So we're going to draw a picture to help us understand this, okay? So we have a beaker here, okay, we got some liquid in it. The liquid is pushing up into the air, I'm just going to label that VP. That's our vapor pressure. The vapor pressure is vapor coming off the surface of the liquid, okay, pushing against the air. Then we have air pushing down. So here's my air pressure. All right, again, VP, I'm just abbreviating. So vapor pressure is pushing up, air pressure is pushing down. When those two forces, those two pressures are equal, whatever temperature that is, that's when the liquid boils. That's the definition of boiling. It has nothing to do with adding heat. If we were to add heat, okay, so if we add some heat to this here, okay, adding some heat to this, what you're doing is you're giving the particles energy so they can push up with greater force. That's why heating boils liquids, because you're increasing your vapor pressure. So when we heat up water, it eventually boils because it's overpowering the air pushing down. But remember the other day I asked you this question, what else could we do besides heating it to boil it? Well, if we can't increase the vapor pressure, what else could we do?
Decrease the air pressure.
Decrease the air pressure. So the easiest way, we're going to write this down, the easiest way to reach boiling, increasing temperature equals an increase in vapor pressure. So that's one way to boil. That's one way to boil. The other way to do it is decrease the air pressure. So these are ways, here, let me kind of do one of these things there. So that's how to boil. How to bring a liquid to its boiling point. You can increase the temp, which increases that pressure pushing up. Because the air pressure is constant. In this room, it's constant. So if we give it heat, you're going to overpower that, and it's going to start to boil. All of these are going to start to evaporate at once. That's what boiling really is, all the particles evaporating at once. So, or we can do this. We can decrease the air pressure. How do we do that?
Go to the top of the mountain.
Go to the top of a mountain or live inside a vacuum chamber, but then you'll die, so that wouldn't work. So, yes, in the vacuum chamber, on Monday, I'm going to take a beaker of water that is not boiling. I'm going to put it in the vacuum chamber, plug it in. All the air is going to get sucked out, so what's going to slowly happen is there's going to be no air pressure pushing down. You will see that water boil. And I put a thermometer in it, and you can read it. It doesn't even come close to 100. It's kind of cool. You can boil water without heating it by decreasing the air pressure. So, just to give you an example here, I think I wrote it down in my notes. So if we increase elevation, oops, sometimes I do that. Increase elevation equals a decrease in air pressure, which means H2O, liquids in general, but water boils below 100 degrees. if you bring a pot of water on a hike, you're hiking up Mount Everest. You get to the top. You want to make some rice. Let's see. Did I write it down? Oh, I thought I wrote it down. I'll look it up real quick online here. But if you go to the top of Mount Everest, so on top here, on top Mount Everest. I feel like that's not the right spelling. I'm really bad at some words.
That seems right.
Yeah, that's fine. Not too good. Let's see. Boiling point of water on Everest. Here we go. All right. Let's see. Really? I gotta click on something else here. All right. Guess I can't find it that quickly here. Could have sworn I had it. It says 71 degrees Celsius. So on top of Mount Everest, it boils at 71 degrees Celsius. So if Morgan is boiling water in this room at 100 and wants to make some rice, and who climbed Everest? Who wants to climb Everest today? Courtney. Courtney climbs Mount Everest. She's making some rice on top of Mount Everest. Whose rice takes longer to cook?
Morgan.
Okay, here's our two scenarios. 100 degrees, 71 degrees. Here's your rice in there, whatever. I don't waste time making rice. Okay? Anyone ever read like directions on how to make rice? How long do you put in boiling water for? Till it's done. I'm gonna say maybe like 20 to 30 minutes.
So you have to boil the water first,
Right.
and then
Then
turn
add-
it down and put it
But
in.
it simmers.
Yeah.
Simmering is boiling. It's still boiling. So is it safe to say 20, 30 minutes? I don't like my rice like super smushy. I like it a little al dente. You know what that means, right?
Yeah, like
No. Like
Like
firmish, soft,
Yeah.
soft, firmish.
it's like a
All
little
right.
bit harder noodles.
What water's hotter? So will it take longer on top of Mount Everest to cook rice, or will it cook quicker because it boils quicker?
Take longer.
It's gonna take probably like an hour. We'll say 45 minutes. Why?
Is that a lower temperature?
It's not as hot. Students always get confused with this question. If it boils first, they're like, oh, it boils first. So it's you can put the rice in first and it starts cooking faster. Maybe it boils first, but it's such a low temperature, it'll take longer. Think of it this way. You bake cookies on 350, right? Let's say 10 minutes. If you bake them on 100 degrees, it's gonna take a lot longer, right? Because the oven's not as hot. It's the same thing with water. So even though it boils first, it's gonna take longer to cook. So your homework, there's a bunch of questions on this. I did want to get back to table 8, but that's okay, I'm out of time. We'll do it on Monday. That's it. Have a good weekend, and we'll talk more about boiling on Monday, and we'll boil that water.